After 2,000 years, some of the most iconic Roman structures are still standing and are in use. The Pantheon, the largest unreinforced concrete dome, a place to honor the Roman gods, is still intact and visited by millions of people each year. There are ancient Roman aqueducts that still deliver water to the modern city of Rome. On the other hand, structures today, built by modern concrete, crumbles and deteriorates just after a few decades. But why? Why do Roman concrete last forever? Were this built by the gods? Just sheer luck? Or did the Roman engineers have a secret ingredient? Researchers from MIT, headed by Admir Masick, a professor of civil and environmental engineering, believe they've cracked the code to the durability of Roman concrete and have published their findings in the journal Science Advances. They gathered Roman concrete samples from an ancient city in Privernum, a 2,000-year-old archaeological site near Rome. The city was occupied by Romans as early as the 2nd century BCE through the 13th century CE. The mortar samples were collected from the bordering city wall. They closely examined the fractured sample in the laboratory by scanning electron microscopy. The examination revealed that these ancient Roman concretes contain millimeter-scale, bright white mineral elements referred to as limeclasts. These mineral features are visible and ubiquitous in Roman concrete and are consistent with other concrete samples dating from the same period, such as those found in Roman-occupied Britannia, Israel, and North Africa. Roman concrete often used a material called quicklime, which is another name for calcium oxide. To make quicklime, you take limestone and heat it up to very high temperatures between 650 to 900 degrees Celsius. This heating process removes carbon dioxide from the limestone, leaving behind the highly reactive quicklime. There are two ways on how to mix quicklime to make Roman concrete. First is slaking, and the other one is hot mixing. Slaking involves mixing quicklime with water first, then waiting for a few weeks or months to dry it out before mixing it with other materials to make Roman concrete. While hot mixing, quicklime is mixed directly with volcanic ash called pozzolana, along with other materials like ceramic fragments, sand, and water. The high temperatures during hot mixing cause unique chemical reactions that form special calcium-rich features. Some of the quicklime particles don't fully react with water during this process and become trapped within the concrete. Both these unreacted particles and calcium-rich features are the limeclasts. It is very important to note that these limeclasts are not present in modern concrete. Modern concrete undergoes a different hydration process by mixing Portland cement, the main ingredient, and water. This process typically leads to a more complete reaction, leaving minimal unreacted particles, hence no formation of limeclasts. The researchers found out that these limeclasts in Roman concrete develop into a brittle nanoparticulate structure that are easily fractured and reactive. When tiny cracks form in Roman concrete, they propagate through the limeclasts. Water can then travel through these cracks and dissolve the limeclasts. This solution then recrystallizes as calcium carbonate, filling the cracks before they can spread further and cause damage. The MIT research team proposes that this characteristic gives Roman concrete the self-healing properties. And that's not all. other studies of similar Roman concrete samples have found out calcite-filled cracks, which support this hypothesis. So to prove that quicklime with hot mixing was indeed the key to Roman concrete's durability, the team created samples of hot mixed concrete using both ancient and modern formulations. They deliberately introduced cracks into these samples and then run water through them. Remarkably, within 2 weeks, the cracks had completely healed, preventing water from passing through. In contrast, a similar concrete sample made without quicklime showed no healing and water continued to flow through it. The results were outstanding. The self-healing capabilities of Roman concrete not only prevented further damage, but also reinforced the material over time. And indeed, these landclasts are the secret to Roman concrete's durability. So what does this mean for the future? It is very exciting to imagine incorporating this ancient technique to our modern construction, from houses, 3D concrete printed buildings, to infrastructures that can withstand centuries. The applications are endless. In addition to improving durability, these efforts could significantly reduce the environmental impact of cement production, which actually accounts to about 8% of the total global CO2 emission, which leads to global warming and the effects we are currently experiencing right now. By harnessing the wisdom of Roman engineers, we can revolutionize how we build and maintain our structures, making them more sustainable and long-lasting. If you're interested about the whole story and interesting things about modern concrete, click here.